Welcome to the 5th week. Now, once again, good morning. Thank you to those who participate in the competition, those who wrote in the issues, and during the exam, absolutely do not forget to write your GitHub nickname, right? And then write if you actually pointed out some typos and everything, because this will help me to understand and to distinguish between those who participated from those who didn't care at all, right? So write anything that can help me to identify and to acknowledge what you have done during the course, right? If you want to, once again, I stress it, if you want to be notified, click on all activity in the GitHub website. Everyone here knows that there is a GitHub website, right? So I stress it every time. I hope this will be absolutely known. Okay, now, last time, we investigated the correlation coefficient. We are talking about the linear relationship between two quantitative variables, right? So we have the population version of the correlation coefficient. This number is only known by God. We, as pure humans, can only try to estimate this number. This is the population correlation coefficient, which we will never know. We can just estimate it. And then we estimate it using what? Using the standard deviation, actually the sample variances of the two variables, and the covariance of the two variables, using a sample of size n. The idea is that as n increases, sample values tend to become more close to the population values, right? Then we have seen that if we have a bivariate sample, and then if our data generating process is normal, then the sampling distribution of this quantity is student t with n minus 2 degrees of freedom. So just to tell you, so we here in the book we have section 7.2, sampling distribution of the correlation coefficient when rho is equal to 0. So this quantity has a student t distribution. Student t distribution is known. We know all the quantiles and everything. So we can perform a test hypothesis and everything. Now, in section 7.3, here, then we have the sampling distribution of the correlation coefficient when the true correlation is not equal to 0, right? And of course, the idea is that if your true correlation is 0.7, in the sample, you do not expect values which are around 0. You expect sample values which are close to the population values. So if the true correlation is 0.8, the sampling distribution must be centered around 0.8. Now, the distribution of the sample correlation coefficient is very intricate because it's very involved from the mathematical point of view. You know, it has the gamma function. It is these are just the first two terms of a Taylor series expansion. And then in one exercise, I ask for those who are brave, I ask to implement this density in an exercise. Those who are brave. Those who are not brave can use functions core PDF or core CDF, which respectively compute the density or the CDF of the sample correlation coefficient. And then recently we have improved this function. For example, see, core CDF. And here, what we have done, if you have the most recent version of FSTA, you should see the so-called the auto-completion with the comments. If you have the most recent version of FSTA, otherwise you don't see it. So, for example, here you see values at which to evaluate CDF. Let us make, for example, a new live script, and let us say compute the probability that sample correlation coefficient is smaller than 0.3 when rho, the correlation, the population, is 0.7 and n sample size, I don't know, is well, 15. Okay, now code. So core CDF, then smaller core CDF 0.3 when rho is 0.7. See, population, you see the auto-completion, population correlation coefficient, right? And n is 15, and that's it. Okay? And then you see the auto-completion, it says sample size. This is just if you have the most recent version of FSTA. Otherwise, these things will not appear, right? They show up in your computer, the auto-completion, right? So you have the most recent version. Okay. Okay, this is 2.08. There is a probability of 2% that even if the correlation is 0.7, that the sample correlation is smaller than 0.3. Of course, let us say, it will have a density, it will have a distribution, and this is the distribution of the sample correlation coefficient. Right. For different values of rho, the true population correlation coefficient, you see, if the true population correlation coefficient is 0.8, then you have values which are centered here, but this is highly skewed distribution. The distribution is symmetric if the rho is equal to 0. To create this plot is something which is very trivial, that you are going to do this plot very easily. You want me to do it together with you? I mean, what would you like me to do? With you? Right. From scratch or start from scratch? Okay. So, okay, so you see the exercise. N is equal to 10 in a 2 times grid of subplots, and the dynamic title to each panel. So here you start writing the values of rho. 0. Okay, how do you write these things in MATLAB? Try 10 seconds. How do you create this vector? Try 10 seconds. Try to think, now don't say anything, and then we will do it. Okay, 0, 0.2, from 2, 0.8, and 0.9. So MATLAB code is raw. 0, 0.2, 0.8, and 0.9 here. Okay? You agree? And this is our row. Of course, every time that you write a code, you immediately check it. Okay. Okay, let us put here. Then, a subplot 2 times 3 grid of subplots. Okay. Shall we do with the subplots or we do it with the tile layout, as we have seen last time? Let us do with tile layout, you prefer? Okay, tile layout. Okay, tile layout, which is flow. So we adjust to the size of the window. Then, let us see, maybe the artificial intelligence now, you see, the artificial intelligence immediately, this is the comment that you have written that tries to understand what you are about to do. Okay, now we accept it, but of course we have to change it. Accept it, but now we have to change it. Okay, plot row I, absolutely not. This is absolutely wrong, because what is on the x-axis here? What do I have to do? What is on the x-axis? On the x-axis here, you have the values, the sequence which goes from -1 to 1, right? So x is equal -1, 0.01, 1. Okay, forgive me, but you know, I've always grown up that a vector is a column vector. So when I create a sequence, I write it in a column. Okay, you see, this sine pi rho I, okay, this is completely absolute. Here I don't want sine and cosine, no, not at all, not at all. However, for I, from 1 to length of row, this is fine. This is something which is fine. Plot x, this is the x coordinate, and here you have core PDF, because this is the density. Values at which to evaluate the PDF is our x. The row, what will be our row in this case? I have to do it for 0, for 0.2, for 0.4, and therefore it will be row I, the ith element of row. Then, what is the sample size n? I write n, and then it's to be defined. N is equal 12, it was 12. Right. Random y value, absolutely not. Okay, and I close it. Row is equal, and this is absolutely fine. On the other end, the title, this is absolutely fine. Yes. Right. Okay. Fine. Isn't it even too easy? Something which is, I mean, something, you may think this plot, no. It's just 2 or 3 lines of code. Right. And what can I tell you now? If you pull out from the output of the MLX, and then we did it with the tile layout, therefore it adjusts. So you see, it becomes 1 times 6. If you do this, then it becomes 2 times 3. If you do this, then it becomes 3 times 2. And then if you keep doing this, then it becomes 6 times 1. And then we do save and save as PDF, export to PDF, that's it. Yeah. But this is actually, this is the power of MATLAB. It is unbeatable, clearly. There is no other software that can do these things in these 3 lines. However, you can do also it with Python, with any other language, but with the guided interface, the copilot which generates the code with this environment, this is really unbeatable. Let us, and you see how the density changes as the true row changes, right? Now, what is the probability that the correlation coefficient falls in a certain interval? For example, when you compute a score CDF 0.7, and then you are computing this interval here, sampling distribution of the correlation coefficient, right? So, in the next exercise, then our density comparison, then you want to see, I compute now the theoretical probability. But now I want to see the so-called Monte Carlo probability. So you run the experiment 10,000 times. How many times empirically do you have the success of your experiment? How many times empirically you have that let us say that the sample correlation coefficient is between 0.2 and 0.3, when the true correlation is 0.6. You see the point? This is the theoretical probability of the density. But then you have the empirical probability. You repeat the experiments 10,000 times, and then you see there's empirical probability. Okay, here you can find everything R density comparison. Let me put here a debug, or otherwise, unless you want me to do it from scratch. So here you have a certain variance covariance matrix in the population. This will be the true variance covariance matrix, so the true variances are here, the true variances will be 1, and the true correlation or the true covariance will be 0.4 high. Then, here I repeat an experiment of drawing numbers. Here, what do I do? Here I draw 7 bivariate numbers. You see, MVN, RND. So you have 7 bivariate numbers, a sample of size 7. And then here, with this sample of size 7, I compute the correlation between these 2 series of 7 values. This is the sample correlation. You see, if you have a sample of size 7, this is the only one thing that you can do. You can apply core, and then you can compute the correlation. So the sample correlation in this case is 0.6762, and the true correlation here was 0.4. Yes, sample values are very different from correlation. You have just a sample of size 7. Okay, then you do step, you redraw other 7 numbers. another sample, and then you compute the correlation. You compute the correlation, and then you have another value of the correlation. You see, now this time the sample correlation is even negative. Can you see it? The true correlation was rho. So the true correlation here was 0.4, but in the sample I observed a negative correlation, right? Then you do for the third step, okay, you redraw other from the multivariate normal distribution with mean 0 and this covariance matrix. You redraw 7 numbers, and then you compute the sample correlation, and this is 0.56. Okay, now this time, right, a bit closer to 0.4. Okay, now you go to line 12, and then you do continue, and then you have done for n-simul. That is, practically, you have obtained 10,000 values of the sample correlation coefficient. Right. You can do the histogram of these 10,000 values in order to see the distribution. Why not? Right. You have these 10,000 values, and then so you can do, let us see, the histogram of R all. Histogram. And see, this is the empirical distribution. Yes, it is true that the sample of size 7, the true correlation is 0.4. This was the true value of the correlation, but sometimes you even had values which were equal to minus 0.8, even if the true correlation was 0.4, you see. And before we were able to compute theoretically this probability. The empirical probability is the fraction of sample which fall inside a given interval. So you see the difference between the theoretical high and the empirical probability. Therefore, you see what you do now, you compute this core PDF, you compute the theoretical density, as we have done before, a theoretical density. Okay, and then we compare with the histogram, normalization with the option normalization PDF in order to scale all the areas such that all the areas of the beans sum to 1, in order to have something which is as close as possible to the density, because the area of the density is 1. So you normalize the beans such a way that their valor area is 1. Okay, then hold on, so the plot that you create does not delete the previous one, and then you do this, and then, okay, you compute this is the empirical, and this is the theoretical distribution. You see the difference. The agreement is exceptional. So we have confirmed that indeed this is the underlying distribution of that. And of course, then you put the X label, Y label, title, and then you want to see what is the theoretical probability that the correlation coefficient is greater than 0.7 when rho is equal to 0.4 and n is equal to 7. You see this option upper, so you compute the right tail instead of the left tail, right? And this theoretical probability here is 0.1964. On the other hand, what is the empirical probability? Among this vector R all, what is the fraction of time that the empirical correlation coefficient is greater than 0.7? You see, can you see this is sum of R all greater than R divided by the total number of simulation, and this is the empirical probability. And then you print it, so you see that the agreement is very, very close. For theoretical probability, this one never changes. Empirical changes at every run. Of course, if you, instead of doing 10,000, you do 100,000, and then you regenerate it with 100,000. Okay, now you see that you are getting closer and closer. These two numbers, okay, actually, you'll never be exactly equal because this density here is an approximation. You see, plus, it's not exactly equal because this comes from a Taylor series expansion. So you are approximating it with a polynomial. So it's not exact because here the number of terms is infinite. From the practical point of view, second order Taylor series expansion is more than enough. But however, even if here you had a very powerful computer and for example, you do 1 million, maybe here it takes 10 seconds, but in 10 years' time, I will be able to show it with 1 milliard. I will be able to show it with billions. Now let us see. Okay, 0.9 theoretical and empirical. So it is never exactly equal to the true one, even in 1 million. From the practical point of view, this is absolutely fine. Okay, however, look now, with 1 million, the agreement is pretty good. Can you see it? Hi. Therefore, here what was important for me now is to stress population and year sample. But what we have seen is the so-called Pearson correlation. In Italy, is very famous, especially in Italy, so-called rank correlation. The correlation among the ranks. So, what you do, you replace the original values of the two variables with the ranks. You know the ranks, that is, you just to understand what is here the rank of this number. The rank of this number is 1 because it is the smallest. What is the rank of this number? Is 2 because it is the second smallest. So you replace each number with its corresponding rank. Right? And then we have the two series of the ranks. Right? And then what you do, instead of computing the correlation between the original numbers, you compute the correlation between the ranks. Of course, something which is robust to the presence of outlying observations, because if, for example, this you have this number, this always gets rank 7, does not change because it is always the greatest, the largest, right? So even if now these values now becomes, the airport is closed so that there is no movements of passenger, still gets rank 1 because it is the smallest, right? So it is unaffected by changes, by changes in the extreme observations. So how do you compute the ranks? You compute the ranks with the tied ranks. Let us see it. So, for example, here you have, I don't know, 2, 5, 8, 3, 10, tied rank, X. Okay, can you see it? That 2 gets the value 1 because it is the smallest. Can you see that 3 gets the values 2 because it is the second smallest? Right, can you see it? Now, we talk about tied ranks because if you have here 2, 5, 8, 3, 3, what is the rank of the 3, 3? Right, but which number do you give? No. No, you give the average. 2.5, 2.5. These are called tied ranks, right? So it should be the second, the third, and then you put 2.5, 2.5. Correct? Now, let us see if you have understood. Okay, did you see it? Because that will be, this is the second and the third. The second and the third position 2.5. Right. So, and then tell me now this thing. If you have 2, 5, 8, 3, 3, 3, what do you get? Second, third, and fourth. No, 2, 3, of course. 2, 3, 4. The average is 3. Oh. Oh, no, okay. However, you check it. Okay, this is very, very easy, right? Therefore, the idea, okay. X1 density estimate. Okay. So, for example, when you load this data, so you load the data that you have seen before about passengers' movements, right? So here you initialize the rank, actually a matrix of zeros, and then with this loop, then you apply tied rank to the 2 columns. So you transform the original variables into ranks. Okay? Well, so you exactly obtain from this to this, right? Of course, here there are no ties, but if just in case if there are ties, you put the arithmetic mean. Okay, and then the correlation between these 2 series, the linear correlation between the ranks is the Spearman correlation, right? So, how therefore can you compute it? Or, if you are lazy, you can do core here on the original matrix, and then here you have type. Type and says, type which kind of correlation you like. So, Pearson is the one that we have seen. And then Spearman is the correlation that we are just between ranks. Right. Therefore, there is not even the need of computing the ranks, because putting type automatically computes it. Now, okay, so let us do with our file firm. So here, what we do here, we load our file, and then we have our x. Our x is the matrix of the 4 quantitative variables, and then you see core x type Spearman. And that's the correlation among ranks. Okay, once you have found, okay, and if you call it with the 2 arguments of output, then you compute the test. The test that the co-graduation, the correlation among ranks, is 0. And so the p-value that between the first and the fourth variable there is no correlation among ranks is 0. You absolutely reject the null hypothesis that these 2 variables do not have co-graduation. So you accept the alternative hypothesis that those who have the largest wages are also those who have the largest seniority. You accept the alternative that seniority is absolutely linked with wage. So once you have this row and the p-value of row, then you do array to table in order to find these tables, okay? So that the output is in table format. So you put the see, row names and variable names are always equal to nomiq, which is the name of the variables that you have extracted. Of course, the nice thing of MATLAB is that if you write here names, shift enter to rename everything. Okay, you have renamed something, shift enter, and then you rename all the things, right? Okay, now let me show you this example. Here in this example, what will be the correlation, the Pearson correlation? Of course, I know that you know absolute, will be exactly equal to 1. And the co-graduation, the correlation among ranks, still is equal to 1, because the smallest corresponds to the smallest, the second smallest, the second smallest, the third smallest, the third smallest, the largest is the largest, right? Now, let us see on the other end this case. Okay, what will be the value of the linear correlation coefficient? Not the one using the ranks. Here, what will be the value of the correlation coefficient? Don't say anything. Try to guess. Then we compute it precisely, of course. I don't want that you tell me the exact number up to 7 decimal digits, but roughly, what will be the value of the sample correlation coefficient here? Say something? More, even more than 0.7, 0.9192, eh? Let us see. Pearson correlation. 0.98, something which is very close to 1. And then, in fact, if here you put LS line, the line, the regression line, you see that the regression line is very, very close to this point. But it's not exactly equal to 1. On the other end, the co-graduation, the correlation among ranks in this example will be equal to what? The correlation among ranks, the Spearman correlation coefficient will be equal to what? Exactly 1. Exactly 1, and now we check it. You see, core XY type Spearman, and then it is exactly 1. Because the smallest is the smallest. The second smallest is the smallest. Right. And now, let us now this y. Y, for example, y, this is y6. y6 becomes equal to 100. Okay. Now tell me something about this. Okay. Now here there is a big outlier that is going to affect your regression line. You see that the regression line is really affected by this big outlier, eh? Of course. In fact, the success in my career has been, I have to thank the outliers, because I'm here thanks to the outliers. So I have to thank, given that the outlier exists, now Marco Riani is here to teach you, because all my publications are about outliers, as you see in my CV. So I'm known. In fact, next week, by the way, I'm invited in a conference in Spain. So next week you are not going to see me, right? So next week, but just for next week, I mean, unless the plane. I mean, something weird happens, or I know, but you are going to see me again, but not next week, right? So next week there will not be no class. Fortunately, because I had forgotten to mention it. No, because I'm in the plane. The only one thing is that I will be in front of the computer, working in the plane, trying to catch up with the 1,000 things that I'm doing, not 1,000, even many more. Have you seen the sample distribution, the number of values of 10,000 values? That's my life, every day. Okay, and here, so the correlation. Here, let us see, the correlation in this case is what? The correlation now will be something 0.6, 0.7, 0.73, eh? But the Spearman rank correlation here will be what? The Spearman rank correlation remains equal to 1. Therefore, you can see that it is much more robust. If a value, even if this one goes to plus infinity, the rank correlation remains exactly as it was. The regression goes to 1 when the...
Yeah. This is our baseline?
This is our regression line.
The last one?
Yes.
When we check the line, all the 5 points, I think that's what I was saying when we graph. Little bit of making up with our here.
Right, perfect. Now, yeah. Okay. This, in fact, the line which passes through these points will be the so-called robust line, the line which is not affected by outliers. And this is precisely, let me see, what is, for example, here, for example, FSTA outlier, let us see. Now, okay, so you see, this is precisely the thing, that you have all the points here, and then one outlying observation here. And then you see that the regression line is corrupted by this outlying observation. What you want to do, you see, a robust fit using the FSTA toolbox, is that you want to have exactly the line he was mentioning. You want to have something which is not affected by the presence of these outlying observations, right? And for example, here you see with these two contaminated observations, and then, well, but I really have, I mean, in the second course, you will learn a lot about robustness. Now the purpose of this course is to do a sort of homogenization. There are people coming from completely different backgrounds, and then I want to put all of you under the same premises, under the same background. So that was the purpose of introduction to data science. Okay. In the next one, we will be much more unleashed. Yeah, right. Right. Now, and what about the correlation, the co-graduation when you have missing values? Because you can have rows which are not completely full. Unleashed. Well, if you have a dog, the dog, and then you have a leash. If you a tagliatelle, no. Yes. Okay. That's our tagliatelle. Have you already had tagliatelle? Have you already had tagliatelle? Okay. Now, of course, by the end of the year, but once that you have tasted them, you'll never forget them. Okay, yes. These are our tagliatelle. Fortunately, it is not, we are not very close to lunch time. Okay, so now let us load this table. Let me do close all, clear all. Okay. Y table, X table. So you see that here they come from these data come from the production process of our most important Italian firm of pasta, which is called Barilla, which is located something like 12 kilometers far from here. If you go in the direction of Mantua, then you'll be able to see it. And these are an important thing is broken. That is the proportion of tagliatelle that are broken. Of course, when you eat tagliatelle, you don't want to see them that they are broken. It's an incredible damage of image if you supply a person tagliatelle which are broken, or at least you allow just a very, very small proportion. So here sometimes there are missing values. So here, what is the correlation between broken, these other tools, and how do you treat the missing values? For example, here, when there is this missing value, but for example, for these two variables, there are the numbers. So, do you delete all the rows which contain missing values, or for each pair you do not delete them? You use all the observations that you can. This is called pairwise deletion. Therefore, just to summarize, well, here you choose. When you do core, once you have loaded the data, and then you have your X. X is just the numbers, the doubles. You see that we have extracted them with curly brackets. So X table is the table. X on the other end are just the numbers. So you do core X. So the first, here you choose the type of correlation. So for example, type, Pearson or Spearman. For example, Spearman. And then it says rows, which says rows. How do you treat the missing values? All, you just use the data that are, all the rows that are complete. In this case, just one missing value for one row is enough to remove that particular row. No. Or on the other end, pairwise, if for each pair of observations if you if you have for these couple of variables, for this pair of variables, you try to use as many observations as possible. Therefore, that's the idea with these two options, right? So type and rows. Then all the rest then is exactly as it was before, right? Now, so let me say, can you see, probably this should be already clear, that perfect linear relationship implies a perfect monotonic relationship. On the other end, a perfect monotonic relationship does not necessarily imply a perfect linear relationship. See it, eh? You see that this implies that. On the other end, if there is a perfect correlation among ranks, and there is not necessarily a perfect linear correlation, inverse linear correlation among the observations. Okay, now you are going to see in the next 50 minutes, now you are going to learn quite a lot about the different graphical representation. For example, yes, you want to start from this or from that, univariate or bivariate series. Have you ever done water ski? Some of you has already done water ski, but it is really very, very nice. Now, when I was younger, it was much more popular, and then you had to do water ski. Otherwise, yes, but now it is much less popular. So, okay, let me tell you what we wanted to achieve. So there is this file which is called graph univ that contains exactly this data. Now, let us see what you wanted to achieve. Okay, this is what you are going to achieve, right? Different possibility of representation of this univariate time series. Now, maybe what is not obvious. So you see, once again, read the table, and then the table, and then you have y, which just contains the double. See, this is something that is data in table format, data in double format. Now, okay. Here you may wonder, why do you create these categorical variables, this categorical variable? And let us see here, okay. The first here you call bar. These are horizontal bars, so you call bar H, horizontal bar. For each one, then F1, and then you go to the help, right? For each one, you go to the help. For example, this bar, let us try to read the help. For example, bar Y, this implies that if you have a bar of 2, 5, 8, then you create a bar with 3 bins, which is the first is 2, the second is 5, and the third is 8, right? On the other end, you see that bar or bar X, which is bar XY, you go to the help, and X draws the bar at the location specified by Y. This implies that if you do bar, for example, 1, 4, 10, you create this 2, 5, 8 at the location 1, 4, 10. You control the horizontal location of the bar. Yeah. Now, Let us try to remove this instruction categorical. So let's say that, so bar h, plot, area is, let me show all of it, let me run all the file, area is this one, and then stairs is this one, and stem is this. So the syntax is exactly the same, just you change the name of the function. However, if you just write cuts is equal to labels, and labels are the, here you see the row names, you see the labels, here you see that labels is a cell array. So cuts is equal to label, and then cuts becomes equal to labels, becomes equal to a cell array. The cell array is welcomed by this bar h. Let us try. Run. Invalid data argument with plot. Line 19. Plots. Here you supply a cell array, and plot does not accept a cell array. In fact, you check plot, you go to the help, learn more, and then you see the plot yx, then you go here, you go to this x, and then x coordinate, and you see data types. What are the data types that are allowed? Here, if it says cell array, then you can supply cell array. If there is not a cell array, no, there is no possibility. So the help is really very well described. But it accepts categorical data, yes. And that's the reason why here we write categorical. You remember the difference between categorical labels and categorical labels, eh? Categorical labels here creates a categorical array of these values, but the order is what? Is the alphabetical order. So if you write the alphabetical order, when you do run, why the first year you have April? Because it's the first in alphabetical order. Why the second is August? Because it's the second in alphabetical order. And look at the stairs, the line, that everything is mixed up. So, categorical, and then the orders is based on labels. Right. The other thing to notice is this horizontal line which passes through the mean. Same thing here. And this is very easy. Bar is something which is called base value. Base value, and then in this case is m through the mean. Right. Because if you don't write it, what you get is that baseline gets you see it starts with 0, right? Then here this is in the first part of the file you have with the subplots. In the second part of the file you have with the tile layout. Right, but what is very nice is that here, if you take this code and then you put it in the copilot and then change the code below from subplot to tiled layout, okay. Shift enter in order to not to do enter, but to go to a different line. Okay, then you supply this code, then it automatically rewrites all the code with the tile layout. You see, that's very nice. but 2, 3, where 2, 3, let us put flow so that it becomes adjustable. But, well, Copilot, of course, if you know what he has to do is exceptional. If you don't know anything, yes, writes the code, but then if the code, you cannot manage the code, then it is a problem. Okay, now let us move on. Let us move on and to the, now there are 2 series. There are 2 series, same thing as before. Let me see, there is some plots here that needs to be discussed. By the way, this may be, this is the rotation thing that this bar 3D, that is very nice. Those who want to know more can do these bars one inside of the other, so you can be unleashed. You can try the different options, right? For example, stacked bars, and in fact the argument here is stacked. And then 100% stacked bars, and you see the idea is that you take this y, you divide it by the sum of the rows, sum y2, and then you multiply by 100. So with this code, you replace the original 2 series to 2 new series whose sum of the rows is equal to 100, right? You divide it by the sum of the rows. And this is, let me see if there is something else. No, this, okay. Now, what about this plot? Have you already done it? This is from gross revenue to net income when you do the balance sheet. So, gross revenue, and then you have a certain of expenses, and then you have the net revenue. Then you remove certain costs, and then you have the gross income. And then you pay the salary, and then you have the operating income, and then you have the net income. So there are particular steps in these balance sheets. And the idea is that you want to see not just how do you pass from this one to this one, but you want to see the intermediate steps, right? So this is called waterfall. So, okay, just to give you an idea, you see that you are very happy about the above number, but you are less happy with this number here, which is roughly generally 1/10 or 1/12 of the original number. Okay, here you toast less. Okay. But however, you have to see during this decrease what are the most important factors. This is what you want, and with this plot you can see it. Waterfall. Okay, so you loaded the data. The function is waterfall chart. And look at this, set as total. So here, set as total, then you have to specify among these numbers, which are the intermediate numbers, which are the so-called subtotals, right? So that's it. Then, you know, well, but then my colleagues of the Department of Economics, they hate this scientific notation. They absolutely they hate it. Is impossible for them to make them digest the scientific notation. But why the numbers are so small? Because they are multiplied by 10 to the 5th. Okay, so and then well, this is the code in order, you know, so that these are really the numbers that they wanted to see. Otherwise, you don't go anywhere if you don't show them the huge number of zeros. It depends on your background. Do you know the funnel graph? Funnel graph is, for example, what happened here in this classroom, because the number of original applications all over the world was 4,300. The number of original applications, of course, there are these agencies that apply all over the world. In fact, there people then continue writing that their name was not written correctly. It is clear how can I think that a person who applies for a data science course cannot write his name correctly into an application? That's it. So then there are pre-screening and so on and so forth, and then this is the final number. So initial applicants, screen candidates, so on and so forth. And here, these numbers, you want to represent them in a funnel chart. These big numbers which you keep reducing, and that's it. So you are among these. So you see, you are, even that you are in this room, in one way or the other, so okay, you are onboarded. Therefore, for these two series, so you funnel chart and that's it. So it is an additional representation. Okay, now density estimate. Okay, are your data normal? These are characteristics of the face, so probably they are normal. How do you do it? You do it with east fit. With east fit, if east fit is called without additional input argument, then it superimpose a normal density. For this variable, you see that it makes sense. For the economic variable, on the other hand, it does not make sense to superimpose a normal fit because they are surely not normal. And so you have a non-parametric estimate of the density. How do you do it? For example, here the thing is that east fit. So east fit, here you control the number of the classes and bins, for example 12 and bins, and then here you specify the distribution. The distribution, okay. So if you have in mind a particular distribution, otherwise you can write kernel is a non-parametric density estimate. Can you see this? He was asking me last time about interpreter none. Okay, so you try to remove this instruction and then you run the file interpreter none, and then here you see that okay, interpreter none. Title, kernel density estimate, let me, okay, remove this one, interpreter none, yes, you see minimal and then the F is put as a small letter because the underscore is the overall symbol of LaTeX that as a subscript, becomes a subscript. So here you say, no, this does not, you see that add properties variable names. Try to see, let me write the transpose, you see. So these underscore has to be interpreted as a character, or what follows the underscore must be written as a subscript. Interpreter none, and then, well, with MATLAB, then everything is, well, interpreter none, and then here, the figure one, so the underscore is interpreted as an underscore. One thing is that fit dist, remember that these routines computes the confidence interval, as we have seen, of the parameters. Then, let us see this plot. So notice here that the x-axis goes from the largest to the smallest, you see? That is reversed. And now you see these so-called gray regions. This is a diagram which is used in astronomy and is called Hertz-Sprung-Russell diagram. Okay. The thing that here I want to point out is that, well, you see all these options. Plots, so this is the standard one. So if you don't write here the O, then it connects all the lines. Let me see. You see it connects all the lines. So you see, for the style is this. Okay, and that's the idea. Now these dots, then what is the marker? And then you see the marker. The marker, okay, you know, whatever is. Then marker face color. What is the face color of the marker? The face color of the marker is K. Whatever, so line style, marker size, and so on and so forth. Okay, so here you have, okay, you can personalize it as you like. Now let me plots 2D, and let me revert to local changes. Plots 2D. Plots, where was plots 2D, right, and then source control, revert to local, discard the changes. So we go back to the original version. Right. Now, the idea is, how do you change from the smallest to the largest to from the largest to the smallest? What would you do? Well, probably up to 2 or 3 years ago, a person would have gone through the help. Up to 2 or 3 years ago, a person would have searched into the Google forums, Google of MATLAB. Probably now people, I'm sure, that will do it with the Copilot. How do you reverse? How do you reverse the x direction in plot? Okay, so you see, set get current axis xd reverse. Okay, then, and which is exactly the code that is written here. However, let me do something different. So here there is the original thing. And then I say set AX is equal to get current axis. The current, you say that is incredible, this thing, that it has automatically anticipated me. You see, AX, and then set AX, X dir normal, or X dir normal, and then here, there is no suggestion. No suggestion yet. No suggestion, let me write X dir. Right. Because I had to run AX, so it knows in memory AX, and so it gives me the suggestion. You see, normal and reverse, right? Normal and reverse. So if you have this thing here, if you apply these two instructions, and then you revert, you see. Or just let me do a small variation, because, okay, it also works with the dot notation. AX, and then X, you see, X direction is equal, and then the auto completion. So you cannot miss it. Okay, plots to depersonalize, source control, discard the changes. Then, let me, how do you do this X region? For example, from 3.5 to 3.6, X region. From 3.4 to 3.5 or whatever. And that's it. Something which is really very, very easy, right? So here you can see that there are these four, these are stars, and there are four stars which are outliers. Now, what you want to see is, you want to have scatterbox plot. So a scatterbox plot is something where you put the univariate box plot for the X and Y. Notice, in fact, that these stars have very, very small value of the X coordinate, and the X coordinate was surface temperature, have a surface temperature which is very, very small, but they are also bivariate outliers, because this is the general shape of the data. And then if you do, if you want to have a robust fit, this is surely what you need to have. But you see, if you want to have a preview monitoring book, for example, monitoring book, Springer, okay, then here you, no, this is not my book. This is, yeah, this is my book, okay. This is my, I don't want to, it is amazing because these people from Amazon are charging these people on the other end, this book is open access. This, it is open access, and this is the GitHub repo with all the files. And then here you have all the YouTube videos about this analysis of all this data, and then you can find also the analysis of this example about the star data that I've shown you now. Now, let me put here a bivariate contour. Bivariate contour is called boss plot B. Boss plot B is a bivariate boss plot. You see it. So it gives a contour which contains the observations which belong to the bulk of the data. And you can see that the outlying observations are completely outside this region. Then you can also have all these bivariate, let us say these, let's scatter with the histograms in the margins. This is function which is called scatter hist of MATLAB. Well, actually, probably this function could have been written in a better way. I really prefer our function scatterbox plot. Scatterbox plot, on the other hand, belongs to FSTA, and these are all the box plot for distinguished by groups. So here you call scatterbox plot as before, so you have an option group, and then you supply your group invariable, right? Now, let me keep going. East 2D loyalty. Let us see, this one is very interesting. Okay, now, suppose that you have a plot like that. Which is the number of visits to the supermarket and then the amount spent. Well, if you enlarge this plot here, you can see that there are many observations. All those which have a very small number of visits, and then the amount spent is very, very small. Here, what you want to have, you call this function which is histogram 2. This is what you want to have, which is exactly the same plot as before. But now you can rotate it. Look, here it says that for the number of visits to supermarket which are in the class 05 and the amount spent is in this class, you have almost 150 people. Can you see the interpretation here? So these are these two plots. So let me delete all the others and let me do layout tile all. So you have to put them side by side, because this is the traditional plot. But here there are a lot of points. How many there are? You can say here on the other end you can. Right, and then you see the positive relationship. You see, this is the projection that you see here. But in 3D, this is what you observe. You see, but with MATLAB you can do all this. With R, you can do, well, it's another story. Now, when you have a so-called regression data, you have a response, and then here you have a set of explanatory variables. And then the plot that usually one has to draw is the plot of y against the different column of a matrix X. Because in general, in multiple regression, you have y and x. And here, do you see outlying observations? Not at all. Do you see points that deviate clearly from the main regression line that you could draw? No, you don't see anything at all. And when you do this fit LM, which provides you with the expression of the estimate, the t-statistics, and the p-value about the importance of the explanatory variables, or when you see the residuals, when you check the residuals of this regression model, maybe you see that there is observation 43 that has the largest residual. But the thing is that if you do now a 3D cloud, Can you see these red points? They are completely inside, or not? They are completely inside the cloud of the data, these red dots, or not? And then observation 43 was the one which had a very large residual. Well, look at this now. And now you can see that these plots are outliers because they are not among the general cloud of the points. And that's the magic of robust statistics, because with the tools of robust statistics, then you can immediately find this data. But in this representation here, you cannot say anything at all. You see, but on the other end, here you see that they are in some way different. So what is the effect that these units have on your model? This is my subject and my topic of research. All right, but once again, look at this original plot. From these original plots, it was not possible at all to see that there were outlying observations here. Now, okay. Certainly now I want to now to finish this okay, let me do hold off. That was a sort of subtle error. You see, that it says adding geographical axis to axis is not supported. Turn hold off. That was a now we are going hold off. Now I tell you, first of all, I want to show you what I want to do. I want to do this. I want to color all the provinces of Italy, right? This is what I want you are able to do. Then here I want that you will be able to do these different plots with different, different background, right? So that everything you can search, you can, and then all these plots then automatically update. Here you can go inside every, different, so you can zoom and everything. And then I would like you to be able to do this so-called geo-icon chart. You see, there is the nail of the electoral participation. The larger is the nail, the greater is the electoral participation. And you see that it's much greater here in north of Italy rather than in south of Italy. Okay? This is the geo-icon chart. So you have an icon, a PNG file. Okay, in the next 10 minutes, we are about to see all these things. Now, so the file that you will find is called plot geoplot. Now, here we have, this is a dataset Cities Italy. We have Cities Italy 2024. Let me close all, clear all, so that we remove all the variables. Now go away. Go away. Yes, it takes some time to go away, but okay, I've cleared everything. So now I have loaded this x is equal to Cities Italy. So these are 12 variables about the characteristics of the Italian provinces. Right. Now, when you load this data, when you do load, first of all, if you have here a warning when you load this data, if you have a warning, means that you did not install the mapping toolbox. Here you need the mapping toolbox. You have a warning, you need to install the mapping toolbox. And then, okay, you get it from home, get as usual add-ons, get explore add-ons as usual. Now, this table X, or this table cities Italy, then we have seen the properties, and then we have seen the, okay, for example, the description, and then tells you what is the description of this data set, information about the variables. So properties, then we have row names, the row names, and then the variable names, and so on and so forth. Okay, so properties, here let us see user data. User data are that additional things that there are. You don't see them. They are additional information. And then you say here there is another table which is attached to the previous table that is contained in the first element of this cell array. You didn't imagine it, that a table could contain inside another table. User data. With the user data, you put all the additional information in a table. Therefore, if you do this, you extract in GTE the geospatial table. And you see, this is another table which is inside this table. And then here, map polyshape, this geo table with all the contours that have been drawn by our National Institute of Statistics. So this is the file that you can download from each country. Each country has this polyshape file. So you see this code of the region, code of the province, and then here the name of the province, and then here shape area, and then the type of province. Okay. Therefore, if you call geoplot, now geoplot of this table, and then you say, how do you want to color the provinces? Color variable, and then you choose the variable. For example, the code of region, and then this is what you get, right? So each province is colored using the value which is inside codereg. Codereg, where is codereg? Codereg is here, right? Codereg. So you see the province for the first region are colored with one, the second region, and so on and so forth. These were the provinces of our of towns that belong to a region which is called Piedmont. Then, so here it says that you have to produce a geoplot. So this is a geotable. This is a geotable. How? Let us check. So you have this GT, this geotable. So the geotable is characterized by the fact that this table has a column which is called shape, which contains all the contours. They have been created by these GIS programs. For example, you wanted to know something more about GIS programs, okay, refer to Giacomo. He knows quite a lot about these GIS programs, and he also played with the contours here of the province of the municipality of Parma. But they are available for each country. Then you have this, and then you load into MATLAB with just one line. Read the geotable, then you put into MATLAB. Here we have put this geotable attached to the other table inside properties user data. Well, here if it is this GT probably you cannot even inspect it. Let me see. Poly shape, if you do double click, no, you see, you cannot even inspect it because it is there are all these contours for each province. Therefore, here it says geoplot, function geoplot, says geoplot. You supply a geotable, and the only one thing that you have to do is how do you color the contours which are inside here, using which variable. And here I've chosen, for example, let us see, for example, if you try to color, use code rip, for example. Here there are just values 1, 2, 3. So you have just 3 colors. Code rip. Code rip, and so then you have just 3 colors. So you see, north, center, and center. Well, let's say no. This is north. Roughly north, center, and south. Just these 3 colors. But this is just to start with, and then you say geo-base map, and then you specify the background you want to see. Colored streets, maybe streets lights. Streets. You prefer this or I don't know, dark water? Okay. Now let us do now here with a color vector, color variable. You see that it is cell J. First, it is bankrupt, it is urban fragility, salary, and it is inside the loop. Solid usual thing, tile layout, next tile, and then geoplot. And then here I say geo-base map type. You see, because I wanted to show you these 4 different type of maps. So you run this thing, and then this is what you get. So which one do you? Then it says none. So, but you see that they are colored. For example, salary. What are the provinces of Italy which have the smallest salary? You see that there is this color bar. Those which belong to south of Italy. Bankrupt, you see, generally smaller in the north. Bankrupt is almost non-existent here in in the very far north. On the other end, however, it is spread out all over Italy. Urban fragility. What are the regions with the highest urban fragility? Those of the south. Now, let me show you also, this is GeoplotFS. GeoplotFS is a part of the FSTA toolbox. You have something which is fully interactive. So GeoplotFS asks you to supply the original table, then the variable you want to show, and then the geotable. see it, what you get. So here you have something which is fully interactive. And then here it says, show label, and then you show the labels of the provinces. Then you have electoral participation, or for example, no, I wanted to have quality of life. Quality of life, and then you see color based on quality of life. Of course, you want to have a better color, you want to associate it with green. It's clear. And then here you do reverse color. Can you see that you have reversed the color? And this is what you are going to expect. Now, map type. Map type. Okay. Light, satellite, okay. Which one do you prefer? Then geographic coordinates on the other end. If you do this is without, and you see that how with all our islands, that is very detailed. Well. The very final thing is that this geo-icon chart. With this geo-icon chart, instead of having a color which is proportional, you have a symbol, a file which is called election, and then here you find this file election. Where do you find it? Come on, order, election, yes, open outside MATLAB. So this is the file, the electoral nail. This is the symbol of electoral participation. Okay, this file doesn't say anything, but inside the geo-icon chart, then you have to put the latitude and longitude. Where do you find the latitude and longitude? You find the latitude and longitude in the user data second argument. And these are for each province, you have the latitude and longitude. So you say, for each province, you have latitude and longitude, and then you put something, you put here this file with the size variable, which is electoral participation. Geo-icon chart, and that's it. Cheat, let me run up to here. This is the very final thing that I'm going to do. Geo-icon chart. No, not this one. Not this one, because it has put here. Let me close all the plots, close all, and let me redo it again. Okay. And this is the electoral participation. Well, I was not very satisfied of this background, and that's the reason why I decided to put a GeoBase map satellite. Okay, this was much better. Okay. This concludes my part. Then now you are about to have a very interesting seminar from Professor Aldo Corbellini about GitHub. He is really a GitHub expert, so I strongly suggest you to participate. So you think it is necessary to put the recording on YouTube, or you think not? Yes. Okay. Okay, thank you.